Okay, so one announcement today is, it is actually not new. So this is tomorrow, right? So when you come, you're going to take the quiz. So don't be late. I load the quiz already. I give you 2 questions, okay? Just 2, 30 minutes. So the first question is about R. Basically read a data set and do something. So how do you prepare it? Homework number 4, okay? That's how. So review it. The second question is basically 1 or 2 exercises from the reading guide. So you know which reading guide you have to read, right? So I just changed some numbers here and there. I changed some word here and there. It's basically, that's that, right? So that's how you prepare. So I hope everything is very clear. Okay. So today is the last day for chapter 4. And we only have 2 topics left. By the way, do you have any questions about this quiz or homework? Oh, actually, I have one more announcement. You submitted homework 4 today, right? There's a homework 5. You can find it in the class website. And that's due by next Tuesday. You have exactly 1 week to do. I wanted to give you this much, but realized that you may be quite busy already. So I decided to give only half of it as a homework, and the other half is simply recommended, okay? So you don't have to actually submit them. Just do a few questions in the homework and submit those. But the entire list is quite long. But all the questions will be important for the exam, okay? So that's why I have this recommended problem sets. Is it clear? So think about this model again. These 2 are part of your data, right? This is something we can observe. Assumption number 2 and 4, no, this is 3. Assumption number 2 and 3 are about this, something you can observe, okay? Now this is something we do not observe. We have no idea what the error is. So that's why it is an error. Assumption number 1 is about the error, something we do not observe, okay? Now this one is very easy. It says xi, yi, the data, your sample, IID. So it has identical distribution. The first person must have the same distribution as the second row. They must be independent. So how do you know that they are IID? As long as you have a random sample, they are IID. Okay? So when you know that you have a random sample, don't cheat. Then you have a random sample. Do you remember this box that we mix it well? And without looking, you're supposed to draw it, right? And you put it back with replacement. So that's an example of a random sample. So if you do that, this will be satisfied. So just kind of easy. Just don't cheat. What does it say? It says that large outliers are very unlikely. So basically it means that as a random variable, x and y has kind of thin tail. Not much surprises. Okay? What if your data has a lot of surprises? What if this is violated? Actually, it's not such a big problem. We can relax it very easily. Do you remember this difference between mean and median? Right? So median is more robust to the large outlier, right? Because for the median, the only thing it cares is how many observation is above and how many observation is below. how above really doesn't matter for the median, right? As long as it does not cross the median itself. So if this is violated, you can simply change your method a little bit. So we drop the least squares, and maybe you can use something like median regression. So there's a median version of regression too. So you can use it, okay? So what I want to say is that these are kind of easy assumptions. You can make sure that this is guaranteed, this random sampling. And if this is violated, there's an alternative. You can just do it very easily. So in some sense, these are not that important in that sense. What really matters, what you really have to remember is this one. So this is something that is very important. So we like to understand what it means. What does it mean? Your errors, prediction errors, are balanced out, right? So sometimes you make positive errors, sometimes you have negative errors, but they just cancel each other. So there is no consistency in errors. So you never consistently overpredict or underpredict, right? So if you sum them up, they disappear. That's what it means. Now, what's the meaning of this? So let me give you an example. Suppose that y is wages and x is education. This is wages. Now, what does it mean? So it means that the errors for each year of education should be balanced out. So in other words, so some part of your sample is high school graduate, right? You only consider them, that small subset of your data. The error for them should be balanced out. Now consider people who graduate college, like 16 years education, okay? Only focus on that subgroup. Errors for that group should be balanced out. Now focus somebody who dropped out of high school and the education is like 11 years or 10 years. Focus on them. The errors for that group should be balanced out. For each group, you can divide using the information independent variable. For each of those groups, errors should be balanced out. Okay? So that's what it means. So which one is more stronger? For the whole sample, errors are balanced out. For any subgroup that you can divide by x, errors must be balanced out. So which one is stronger? If this is true, do you think that this must be true? The high school graduate, errors are balanced. College graduate, errors are balanced. The master students, errors are balanced. That's the case. Do you think that this holds? Can you raise your hand if you think that that's true? How about this? Is it true? Overall, they just canceled away. Okay? For everybody. You only focus on the high school graduate. Is there a guarantee that their errors are canceled out? So this is not true, but this is true. So in that sense, this condition is much stronger than this condition. In other words, if you have like data or sample or cases, whatever, that satisfy this condition, it is going to be a small subset of the cases where you have this condition satisfied. Okay? Now let me give you an example. I'll give you 1 minute. And please try this. try it. So if the conditional mean of the error is equal to 0, the unconditional mean of error must be 0. Balanced out overall. The thing is that this one actually tells a lot more than this. So basically what it says is the error term is centered correctly, centered at 0, right? That's what it says. But this condition tells a lot more. So let me remind you one thing. So there's an exercise we solve together, and the exercise says do you remember this exercise? Now it doesn't have to be 0 as long as conditional mean of u given x is not a function of x, as long as it doesn't depend on x. So it can be 0, it can be 1, it can be minus 100. Doesn't matter. The covariance between two terms must be equal to 0. Okay? So this condition, the regression assumption 1, the first assumption, actually says this, of course, the center about the error, but it tells a lot more. Actually, it tells something about the covariance relationship between the errors and independent variable. Now, what we know from this exam, exercise, this is the assumption, right? If the assumption holds, then covariance must be 0. So in the regression, you have to make sure that the covariance of the error and independent variable is 0. If that is violated, what happens? The assumption is violated. Now we cannot trust the regression outcome if this is the case. Okay? Now, do you remember how to show this? You want to try? We don't have enough time, so I'm not going to try right now. But we did it maybe 2 or 3 weeks ago. So if you have time, please review it. This may be useful for your exam, not for the quiz. Okay? Now, we are saying that this conditional mean 0 assumption, the first assumption is something about the covariance between the error and the independent variable. So let's think about the relationship. Now, between these two, which one is stronger? So it means that if the conditional mean is 0, the 0 covariance is guaranteed. So in that sense, this one is stronger than this. Does it make sense? It does not go to the other way. Sometimes you have 0 covariance, but somehow this assumption can be violated. It doesn't go the other way. It only flows to one way. So let me just write it in this way. All the cases where conditional mean is 0, there are a lot more cases that you have a 0 covariance. Okay, so that's the relationship between two. Now we have actually one more concept about the relationship between two. That's independence. Let's think about u and x are independent. In notation, you can say u and x are orthogonal. So basically, we have these three kind of concepts about the relationship between two variables. One is the independence. Second is zero covariance or zero correlation coefficient. Third is conditional mean zero, or conditional mean not dependent on this conditioning variable. Out of three, this is the strongest one. Okay? So independence is a really small subset of the regression assumption 1. So what is happening is this. This is kind of a concept that we know very well, right? So the independence means that the joint probability distribution is equal to the product of two marginal, right? Or the conditional probability is equal to the marginal probability. If that's the case, we say that two random variables are independent. So we understand this concept very well. But this is too restrictive. There are only small cases that satisfy this assumption. So it is not really useful for the regression. It is too strong for the regression. Okay? So we need something slightly more inclusive. Now, zero covariance is again a very natural concept, and we understand it very well. And it includes really many different cases. But unfortunately, it is too weak. It's not strong enough for us. For the regression, we need something slightly stronger. Zero covariance, okay? So what is the right balance between this strong assumption that only includes a few cases and this weak assumption that includes a lot of cases? If you assume this, you can actually show many things very easily. Everything is very easy once you assume that X and U are independent. But somehow it's too strong, too restrictive. This is too weak. There are not many things you can show. Okay? The math just doesn't work. If the only thing you know is zero covariance. So the right balance is this guy. Okay? This is just good for the regression. So that's why it is our assumption number 1. Okay? But basically what it says is errors and independent variables are somehow unrelated. There shouldn't be any systematic relationship between them. Okay? That's what it says. Now, in the lecture note, there are more. So, for example, I showed why independence implies this, for example. Okay? The lecture note explains why this is a subset of this one. So if you wonder, you can read it. Also, the lecture note, maybe not this one, but something we did before explains why this implies zero covariance. So if you want to know more, please read them. Okay? But the most important one is this relationship between three. So that's the assumption. Once we have this assumption, I can tell you a few more things. Now let's think about this. Now suppose that this assumption is true. And this is the linear regression model, right? So take the conditional mean on both sides. So you can take the conditional mean. Now beta null is a constant. It's unknown, but it's a constant. So you can put it out, right? Same for beta 1, you can put it out. What about x? It is conditioned on x. X is known. It's a constant, so you can put it out, right? So you can write it this way. Now the assumption says the last term is 0. Right? So what do we know? This population regression line is actually the conditional mean of y given x. Okay? So that's one way to understand the regression line. is actually the conditional mean of income given age. The conditional mean of test score given class size. Okay, that's what this regression line means. So that's one observation. The regression line is the conditional mean. The second observation is this. Now this regression line is nothing but the conditional mean of y given x. So we can rewrite the regression model in this fashion. So in our assumption, y can be explained this way, right? Under this model assumption, we know that this regression line is nothing but the conditional mean of y given x. So you can rewrite it this way. So what does it mean? Your outcome, the test score, can be divided into two components. One is the conditional mean part. So this is something we can calculate from data. And the other is error, something we cannot calculate at all. So this is something we can control. This is something out of control. Okay? So that's how you divide your outcome variable. Now there's a more about this, but that's in the lecture note. So please read page number 1 and 2 of the lecture note. Now, do you have any questions so far? So that's the 3 assumptions, okay? So from today, please remember them. So if I say, what is the regression assumption 1? Then I expect an answer like conditional mean of error given independent variable must be equal to 0. That means that errors and dependent variables are unrelated. There's no relationship between them. Now again, this is our assumption. So we suppose we imagine that if you have everything, everybody in the population, then this must be true. Okay? It's purely an assumption. So beta null and beta 1 are the intercept and slope of the regression line for the population. For everybody, you can imagine. We do not know their value because we do not have any population. If you have population, then you can find it out. But unfortunately, we do not know. So these are unknown numbers. So what we do, we draw one sample, and we can run the regression and calculate these hats, right? And the last topic is what is the sampling distribution of these hats? So basically the same story. Goes that there's this huge population and what is unknown is, for example, beta 1, the slope of the regression line. Because we do not know beta 1, we draw a random sample. Random sample means we have no idea where the sample comes from, right? Suppose that you draw a random sample here, then you can get beta 1 hat. But the point is, your friends can draw a different sample over here and may have different beta hats. Right? Do you remember this box that I draw the random sample from the population with the replacement? So whenever I draw a sample of these cups, the realization, the actual sample can be different, right? And the sample mean has different value for each different draw, right? So that's the meaning of different sample produce different beta hats. So beta hat, in that sense, is a random variable. It's random because you never know the value of beta 1 hat until you draw a sample. Once you draw your sample, then you can find out its value. If you draw another sample, you have a different value. You can keep repeating. So beta 1 hat has a distribution depending on the sample. So if someone else draw sample like that, he or she has a different beta 1 hat. Do you remember this thing, the mean of the mean? that we talked about? The center of the sample mean. Do you remember that? Do you remember the variance of the sample mean? So I basically talk about the same thing. So we can think about the mean of beta 1 hat and the variance of the beta 1 hat. Does it make sense? If you repeat this exercise many, many times, you can draw a different values. So the beta 1 hat has a distribution. So the claim is, there are 3 claims. So I'm going to write about beta 1, the slope. The same thing holds for the intercept 2. So the mean of the beta 1 hats, those values of beta 1 hats for different samples is equal to the population slope. Okay? So the easier version of this, the chapter 2 version of this was mean of the sample mean was the population. Right? Do you remember this from chapter 2? If this is true, we say that the beta 1 hat is unbiased. So that's the first claim in the book. The second claim says this. So the beta 1 hat, the value from your sample, is very close to the beta 1 from the population if you increase your sample size. So this one is actually quite easy to imagine. So suppose that you make your sample bigger and bigger, bigger and bigger. What happens? If n goes to infinity, eventually your sample is going to be as big as the population, right? Difference will be very small. So the slope from your sample must be very close to the slope from your population. Does it make sense? So imagine that your sample becomes bigger, bigger, bigger. Eventually covers the population, right? So this must be true. If this is the case, we say that it is consistent. So that's claim number 2. Claim number 3. Now this guy is trickier. Now beta 1 hat has a distribution, different value. So we can think about the mean and variance. So the first claim says mean of beta 1 hat is equal to the population slope. What is the variance? So everything I write is in the book. I think there is a box, some kind of box to summarize all these things. Okay? So you can easily find it. So that's the variance. So it depends on the variance of x independent variable, and the variance of your x minus its mean times your error. It's kind of, you multiply your independent variable and your error first and calculate the variance. Okay? So these will be just some kind of constant that we do not know. What matters is the variance is 1 over n. So as you increase your sample size, variance of your beta 1 hat must be smaller and smaller and smaller, proportional to the sample size. Okay, so that's 3 claims. So normally, like a few years ago, when I made this kind of claim, I used the mathematics and actually proved it. And the proofs in the book. So if you wonder how to make such a claim, you can find out the book. It's actually not that hard. So everything you have to know about beta 1 hat is already known. It's like beta 1 hat is the ratio of covariance and variance, right? So you can use that fact. And then you use the law of iterated expectation. Then you can show everything. Okay? It is that simple. So, but now we're not going to do that. Instead, I'm going to use simulation. And that the simulation does not prove any of this, but at least I hope that it convinces you that this must be true. Okay, something like that. So I'll give you maybe 30 seconds to write it down somewhere in your notes, because we have to check these 3 facts, right? So write them down somewhere so that you can easily go back, and then we are going to have an R session. So hopefully using the simulation, we convince ourselves that these 3 things, this unbiasedness, consistency, and the variance of our estimator something like that. Now let me talk about this first. So what is this .r? It's just a text file. Okay, that's it. So in this text file, I just made up the extension .r to emphasize that I write it for R. Okay, this is a text file for R. Just call it R document or R code. So basically, it has a line by line R comments with some comments, because tomorrow I'm going to forget why I have this comment here and there. So as you can see, so this is a comment. Okay, I'll skip this line because it starts from this line. This is a R. This is a comment. I have to really clear. So this is my comment. This is a note to myself or note to my friend. Okay, so if you want to write a comment, you can use it. Now this is our comment. So basically, line by line, I collect the R functions, R command I like to use. So why are you going to do that? Because basically, writing a program means that you repeat the many things. Like read.csv, you just repeat it every time, right? And lm, y, and x, repeat it every time. So it saves a lot of time and energy if you make a text file and write down the code, read the CSV in there, and just open the code later, right? And this is easier to send to your friend. So when somebody says that he's writing a code, computer code, what does it mean? He's working on a file like this. Keep adding a new line, making comments here and there. Okay? So that's what we are going to do from now on. Okay, so that's that. So how do you open it? Again, you just click this, open script. That's it. Now, what is this data? So this is data from some kind of income survey. The CPS means, so every 10 years, the country does some kind of census for everybody, right, for the whole population. But to find out the unemployment rate, something like that, it cannot do the census like every month. So what it does is, it has a small random sample out of the total census and follow that small sample every month. So that's how you find out the rate of unemployment or the mean wages, mean income, things like that, okay? CPS is such survey from the United States. So it's a small data set we have. This is the year, so it's all from 2008. The first variable, AH, is the wages per hour. So the first person makes $38 per hour. Second person makes $12 per hour. Because the working hours varies a lot across individual. Some people are working for like 60 hours per week. Some people do that only for 20 hours. So we tend to compare the hourly wages, not the monthly wages. The bachelor is a dummy for the college degree. So 1 means college graduate. Female is a dummy for gender. 1 means female. 0 means male. Age is age. So this person makes $8.20 per hour. Doesn't have a college degree. A man. And 30 years old. Okay? That's how we know about this guy. Okay, so that's the data set. Now you probably understand the line by line quite well. So what does the first line does? It reads the data, right? So how to run it? So I make a block. So I just use a shift and the arrow, the downside arrow. And then I can, so there are two options. If you click this, it runs everything in the script, in this text file, or you can just run line or selection. The shortcut is Control R. So that'll be easier. Why don't you click it? Does it work? It does not, right? So what's the problem? So we have to change the directory first. So change my directory. I make a block and I Control R. I just read my data set. Now what does it do? This line? When do you use it? So you find out the variable, right? What variable is there? And when do you use this comment? Dimension. This. So how many variables do you have in this data set? 5. How many observations do you have? 7,711. Okay? And we can attach our data set. Now it's a sample, right? It's a small survey from the United States. We can, of course, run the regression. So to make it simple, from now on, the dependent variable is the hourly wages, how much you make per hour. Independent variable is age, how old you are. Okay? So you can run this regression. Now what does it mean? So what's the meaning of this 0.6? As you get 1 year older, what happens to your wage? You make 60 cents per hour more, right? You make additional 60 cents per hour. Now, for us, this is what I really want to say. It says, let's regard it as the population. Can you imagine that? What does it mean? Now this CPS-08, don't be confused. It's a sample, it's a small sample from the population. So the population here means every working age people living in some country, right? For example, for this exercise, it's United States. So everybody between 22 to 30 something in the States, that's the population. We don't even know how many are there. So that's the population, and this is a small sample, right? But for our purpose, just to make sure that we understand the meaning of the sampling distribution, for a while, for the next 30 minutes, we assume that the CPS-08 is a population. And then I'm going to draw even a smaller sample. Can you imagine that? So from this exercise, we assume that CPS-08, our sample, is the whole universe. Okay? And then I'm going to draw a sample from it. From that moment, what is this value? 0.6. Under the assumption that this is our universe. This is the value of beta 1. Because we have a population, we know the true value of the slope and intercept. Does it make sense? Because what is the meaning of beta 1? It's the population slope. Once you have the population, you should know this value. Okay? Hypothetically. This is not the population, so it's not the true value. But for a while, let's assume that that's the case. Now the question is how to draw a sample from it. So for that, we are going to use this function. For this, can you type it actually? So 1 to 5 is a vector. The function sample, draw a random number from a discrete uniform distribution. With equal probability. So if you want to draw just one, you can say sample from 1 to 5, that's the first argument, comma, the second argument is how many draws you want. So if you say 2, then you can draw 2. Now you realize that we never draw the same number twice, right? What does it mean? It is drawing without replacement. What we want is draw with replacement. Because that's how you draw a random sample, right? So let me just draw, for example, 4. Then you can repeatedly draw 2 twice, 1 twice, 5 3 times. Compare this against this option. Never draw the same number. So if you have to draw 5 numbers, then it's just not interesting anymore. But if you allow the replacement, it becomes interesting again, okay? So draw a sample, we are going to use this function. So this is my idea. So we know that there are 7,711 workers in my universe, in my population. So I give them number from 1 to 7,711. Okay? From that number, it's like, everybody has a number in their back. And then I'm going to draw, for example, 10 numbers with replacement. And I call it index. Okay? So what it means is that from the universe, I draw a sample of 10 in this way. So this person is selected, this person is selected, this is selected, something like that. So I just draw a very small subset. Make this sample. It has to be true because we draw a sample with replacement. That's how you draw a random sample, right? Now imagine these two lines. What do I do? So I draw from this universe, from my population, 200 workers with replacement at random. Okay? So they are going to be my sample from this population. So I select only those who belong to this sample and make a regression. Can you imagine that? Why don't you run it? Now, let me just show you. My index has 200 random numbers. Some of them may be repeated because I draw it with replacement. So when I say age of index, I only select ages for those who are selected. 200 of them. Same for hourly wages. So we have 200 observation for the dependent variable, 200 for the independent variable. And of course, you can run the regression. We have 200, so it has to be a little bit bigger. Now, can you see the difference between two numbers? So A was a regression from everybody, right? From the universe. So this is beta 1, the true value. What is this? This is my beta 1 hat from my sample. So here, my beta 1 hat is what? 0.66. Are they equal? No. Why? Because to produce it, I use 7,711 people. To produce it, I only use 200. So they shouldn't be the same, right? Because this is for the population and this is for the sample. Now, my point of having this sampling distribution means this. If I draw a different group, so if I draw the index again, and then run a regression, and get the coefficient. Now it's very, the beta 1 hat is very different. Take a look at this. They're not the same. So the value of the beta 1 hat depends on the sample, right? So in that sense, it is random. If I do it again, it means I draw another sample, run the regression, get the coefficient. Again, it's different. If I collect all these different values, I have a distribution. Okay? That's what I want to do right now. Now, I just tried it like 3 times, but I'm going to repeat the same job for a lot more, like 1,000 times, maybe 1,000,000 times. With a computer like this, we can do it very easily. So let me show you how to do it. So the question is, what is the sampling distribution of the regression coefficient, things like that, okay? So to find out, our small simulation will go like this. So I define L, which is the number of repetition in simulation. So I set it 1,000, means that I'm going to draw a sample 1,000 times, okay? NS means sample size. Sample size N in my small sample S. So that's going to be 200, right? Now, what does it do? So it creates an empty matrix, L by 2 matrix. It's empty in the sense that every element is 0. Why don't you try it? Control. Oh, L is not defined. So A is just a big matrix. So why do I need it? I'm going to collect all the results in there. Now this is tricky. Because of the time constraint, I'm not going to explain what it does. But you can use the time after this class to figure it out. Okay? There is some comment there, right? So we are going to make the whole block. And we are going to run the whole thing. But imagine this. Let me just explain very briefly. For function in R means repeat. What is inside? So what to repeat? I make an index. I draw a sample, which means I draw a smaller sample like that. And I run the regression. I get the coefficient and save it in A. And I'm going to repeat this job for L times, 1,000 times. So I just repeat this exercise many, many times until it reaches 1,000. And that it is stopped. So why don't you make a block, the whole thing, and run it. Somehow it's very slow. I don't know why. Usually in a PC, things like this takes less than a second. I'm pretty sure that it is because in my computer there's a lot of things going on right now. So the CPU is very busy. Wow, it takes forever. Oh no. No, it's done already. So beta null hat is saved in the first column. Beta 1 hat is saved in the second column. So to see the beta 1 hat, I can do this, right? So every low and the first column. So that's 1,000 realizations of beta 1 hat. So this is beta 1 hat. This is beta null hat. And the distribution looks like this. Now, this is a sampling distribution of beta 1 hat. Okay? The sampling distribution looks like this. Now, let's check those three things one by one. We cannot check everything, but at least we can check the first claim. Unbiasedness. What's the claim? The mean of the sampling distribution of beta 1 hat is equal to beta 1 from the population. So what is beta 1 in this exercise? 0.6. Now, is the mean of the sampling distribution equal to 0.6? It looks like, right? So why don't I say mean of so it's actually very close. The beta 1 from the population is 0.604. The mean of the sampling distribution of beta 1 hat is 0.605. So that's from the 1,000 repetitions. If you do it for 1 million, 1 billion, I'm pretty sure that it's going to be very close to this number. Okay? So we checked one thing. So that's the meaning of unbiasedness. Your estimator is unbiased. That means that the histogram of beta 1 hat has a right center. Okay, this guy is centered at 0.6. Same for the intercept. So that's what it does. Now, what's the meaning of consistency? So let me stop it after this. So this exercise is, so consistency means if you increase your sample size, then your beta 1 hat becomes closer and closer to the truth, right? So here, I increase my sample size to 800, and then repeat the whole thing, okay? I save everything in B. So let me do it. Now the sample size is much bigger for this. So when I draw this sample, each sample is 4 times bigger than previous one. And then we can draw the histogram that is overlapped. So P1 is the histogram from the first exercise when the sample size is 200. And P2 is the histogram from the second. And the sample size is 800. Let's compare them. Now what does it tell you? The outer one is the histogram distribution of beta 1 hat when the sample size is 200. This one is a distribution of beta 1 hat when the sample size is 800. What do you see? The variation is much smaller, right? As you increase your sample size, you have much less variations, more concentrated around the truth. Now, what if you increase your sample size even more? Well, we cannot do everything because of time constraint, but why don't you try it? So that's my claim here. So here, the sample size is again 4 times bigger. 3,200. You can make this plot. Now, this is when the sample size is 800, 3,200. Now, it's much smaller, right? Has less and less variability, means that it becomes more and more precise in each learn. Okay, so that's the meaning of consistency. If you increase the n more and more, it becomes more and more shrink around the truth, 0.6. So that's the claim number 2. Okay, so let me stop at this point. What about question number 4? So why don't you try? Okay, so we're not going to come back to this one, but if you want to, you can try this. Okay, so tomorrow there is a quiz, so study hard. And as I said, there is a advice or some kind of guideline in the class website, so read it.